We've looked at ionic bonding, and now we're going to look at covalent bonding. There's compounds that don't form ions because one element can't pull electrons off the other. They have about the same strength of pulling on electrons, and so they can't transfer electrons. What they do instead is share electrons. And when electrons are shared, you form individual units that we call molecules. You know of molecules, for instance, water is a molecule of oxygen and two hydrogens, and that two hydrogens attached to an oxygen move as a unit. Carbon dioxide, one carbon and two oxygens attached to the carbon and they move as a unit. You can pick up individual molecules. We have something called diatomic molecules, and these are elements that exist as molecules. So diatomic just means two atoms. There are a lot of elements that occur as individual atoms. You could isolate an individual atom, but some elements don't exist that way. They're highly reactive if they're existing as atoms, and those are the diatomic molecules. So in their natural state, they have two atoms stuck together, kind of like a Twinkie, two Twinkies in one package. The diatomic molecules have two atoms in one package. These are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. There are 7 of them. How do you remember them? Well, the 7. Hydrogen is in the upper left-hand corner, and then starting with element number 7, nitrogen, the rest of the elements form a little 7 kind of in the corner of the periodic table. Look at a periodic table and you'll see. So what we're going to do is we're going to look at some diatomic molecules. If we look at hydrogen, we can't form ions because the two hydrogens pull equally on electrons, so one can't pull an electron from the other. We're going to look at fluorine and see what happens when two chlorines collide with each other. So here's a fluorine, and I'm writing this as a Lewis dot structure so as to simplify the picture. So fluorine has 7 electrons in its outer shell, and so does this fluorine. Let's have them collide. And if they collide, these two electrons can overlap. And when this actually orbitals, overlap. And when those two orbitals overlap, this one electron can actually be on this fluorine and this fluorine at the same time. And the other electron can be on both fluorines. And if we draw it like this, you can see that this fluorine has 8 electrons and this fluorine has 8 electrons. That's an octet, and we know that that gives stability. These 2 electrons we say are shared, and we call those 2 electrons a bond. And then we have these other electrons on the outside. This fluorine has 1 bond and 3 non-bonding pairs of electrons. But it's stable because each atom now has an octet. We draw the bond as a line. So a line means 2 electrons. The 2 nuclei are pulled together in a bond because there's a positive nucleus, 2 electrons between, and then a positive nucleus. And those 2 electrons in the bond are really highly concentrated between the 2 and draw the 2 nuclei together. You can have double bonds. Oxygen has 6 electrons in its outer shell, and what it actually does is share 2 pairs to make what we call a double bond. You can see that this oxygen has 1, 2, 3, 4, 2 pairs of electrons that are non-bonding pairs, and then it's got 2 bonds here. So all together, this oxygen has 8, and so does the other. And we draw the double bond as 2 lines. Nitrogen actually forms a triple bond. It has 5 electrons in its outer shell. So if I look at how it's arranged, you have a non-bonding pair and then 3 pairs shared between the nitrogens. All 3 are on both nitrogens. So look, this nitrogen has 8 and this nitrogen has 8. So it gets stability. We call that a triple bond, and we draw it as 3 lines. You cannot have any greater than a triple bond. And no atom can have more electrons than 8. The triple bonds are stronger than a double bond, which is stronger than a single bond, and they are shorter also. Triple bond is shorter, then comes double bond, then the single bond is longest of all. To draw Lewis dot structures, I just showed you diatomic molecules. To draw Lewis dot structures of molecules, it gives us a sense of what the molecule looks like, and it'll even give us geometry. We only use Lewis dot structures when we're looking at covalent bonding, non-metal to non-metal bonding. The Lewis dot structure is what gives us models in biology. So you see these little cartoon drawings in biology, and they're cartoon drawings of molecules. Those cartoon drawings come from us doing a detailed analysis of the bonding and being able to determine what the three-dimensional shape is from that detailed analysis of the bonding. In all of our Lewis dot structures, all the atoms have to have an octet for stability to occur, except for hydrogen. Hydrogen will always have just one bond and no non-bonding pairs. When you look for an octet, you count all the bonds that are attached to it. Each bond is 2 electrons, and then the non-bonding pairs. So there's a more complicated way of doing Lewis dot structures, but we're just going to use the simple way. And the simple way is to use these little rules that carbon always has 4 bonds. So it can be a single bond and a triple bond, or 2 double bonds, or a double bond and 2 single bonds, or 4 single bonds. And the other elements in its column will do the same thing. Oxygen always has 2 non-bonding pairs and 2 bonds. So 2 single bonds and 2 non-bonding pairs, 2 single bonds and 2 non-bonding pairs. And the other element in its column does do the same thing. Hydrogen always has 1 bond, and a hydrogen separated from a molecule is almost always going to be what we call a proton, hydrogen with a positive charge. And then the halogens always have 3 non-bonding pairs and 1 bond. Nitrogen has 3 bonds and a non-bonding pair, and phosphorus does the same thing. So to draw a Lewis dot structure, what you do is you take the formula and you put the first atom in the formula that is not hydrogen. Hydrogen can never be in the center of a molecule. And you place that down as the central atom. Then you surround the other atoms around it and attach them with bonds. If there's more than 1 carbon, the carbons are all in the center and bound to each other. And then you replace the remaining atoms around all of them. If you ever have hydrogen first in the formula, you have to place it on an atom that is attached to the central atom. So once you have this little skeleton of how you put the atoms down, what you have to do is connect all of them by single bonds. So you wouldn't like make a triangle necessarily, but let's say there's a carbon with 4 chlorines attached. You would attach the carbon to all the chlorines. Then you add the non-bonding pairs. And if it turns out that one of your atoms needs more bonds, then what you do is you take away a non-bonding pair and you make it into a double, or if you have to, take away another non-bonding pair and make it a triple bond. So let's look at this. Here is carbon tetrachloride. So we put carbon in the center, and we surround the carbon with the remaining atoms. Now we put in the bonds. Now we're going to remember the rule is that carbon has 4 bonds and the chlorines have 1 bond and 3 non-bonding pairs. So after putting the bonds in, then you say, okay, well, we need non-bonding pairs now. So each chlorine gets 3 non-bonding pairs. We're done. Go ahead and try this molecule and see if you can do it. First thing to do is put carbon in the center. We add the remaining atoms surrounding the atom. Notice hydrogen is not first in the formula, so we don't attach it to an outside atom. It's just attached to the carbon. Now we add our bonds. Let's consider our rules. We're through with adding bonds to connect them. Carbon has to have 4 bonds, and oxygen has to have 2 bonds and 2 non-bonding pairs. So I have to have carbon have another bond and oxygen have another bond. And I have to put in the 2 non-bonding pairs. Since this and this both need a bond, I'll make it between it, and now I'm done. Notice every atom except for hydrogen has an octet now, so it's stable.